will be able to describe armature windings, explain the lap and wave type of armature windings and their selection criteria, define equalizer rings and dummy coils. Every rotating electrical machine has an inevitable part called as an armature, which consists of the armature core with poles and slots, and armature windings accommodated in those slots. These armature windings are nothing but an arrangement of current-carrying conductors to produce EMF in the machine due to the relative motion between the windings and the starter magnetic field. Thus, these windings play an important role in the explain the lap and wave type of armature windings and their selection criteria, define equalizer rings and dummy coils. Every rotating electrical machine has an inevitable part called as an armature, which consists of the armature core with poles and slots, and armature windings accommodated in those slots. These armature windings are nothing but an arrangement of current-carrying conductors to produce EMF in the machine due to the relative motion between the windings and the starter magnetic field. Thus, these windings play an important role in the operation of an electrical machine as a motor and as a generator. The armature windings can be categorized into two types, depending on their winding arrangement and connection to the commutator. They are lap winding and wave winding. Let us start with lap winding. In this type of winding, the completing side end or the back end of a coil is connected to a commutator and to the start or front end side of the successive coil under the same pole pair. This process continues for the remaining of the coils. It can be observed that the coils overlap each other in this type of winding method, and hence the name lap winding. Therefore, the number of parallel paths A of lap winding is equal to the number of poles P. The illustrated armature winding is called as progressive winding, as the winding progresses in the direction of the coil wound. The other way of winding is called as retrogressive winding, in which the winding progresses in the direction opposite to that of the direction of coil winding as illustrated. Here, the displacement between the sides of a coil measured in terms of armature conductors is called as the back pitch YB. Front pitch YF is the displacement between the completing side of one coil and the starting side of the successive coil measured in terms of armature conductors. We can see that for the progressive style winding, the back pitch is greater than the front pitch, and the front pitch is greater than back pitch for the retrogressive winding. The distance between the beginning of one coil and the beginning of next coil, measured in terms of armature conductors, is called as the resultant pitch YR. The commutator pitch YC is the distance between the commutator segments in which the two ends of the same coil are connected. For the progressive and retrogressive windings displayed, the two ends of the coil are connected to the adjacent commutator segments, and hence the commutator pitch is equal to 1 and -1 respectively. The displayed windings are of the simple type of lap winding, as the distance between the two consecutive coils is equal one commutator segment. If the distance between the two consecutive coils is equal to two commutator segments as illustrated, then this type lap winding is referred as the duplex winding. These terminologies are essential in order to design the armature winding. In DC machines, due to the possible dissymmetry in the pole's structure, there is uneven distribution of flux per pole and EMF in the parallel paths, which in turn causes unequal circulating currents to flow in the armature through the brushes, causing overheating and severe sparking during commutation. Hence, equalizer rings are used to avoid such overheating and sparking. Equalizer rings routes the circulating current to the coil itself and helps in producing equal EMF in the parallel paths, thus resulting in sparkless commutation. As we have seen, in the lap-type winding, the coils overlap and are parallel to each other. Hence, the current capacity of each lap windings gets added, providing higher operating current. Therefore, this type of armature winding is used in applications requiring high current and low voltage. One such application is the welding generator machine, which produces higher current for welding purposes. A dynamo is another application producing high current normally seen in the bicycles. Now, we shall learn about wave windings. In this type of winding, the completing end of a coil is connected to the starting end of another coil under a different pole pair, moving ahead, avoiding overlapping. This process continues for the remaining of the coils. The appearance of this coil winding resembles that of a wave, and hence the name wave winding. Here, regardless of the number of poles, the number of current paths or parallel paths is always equal to 2. Therefore, even in the presence of unequal flux distribution due to any dissymmetric poles, the EMF in both the parallel paths will be the same, as both the coils are affected equally by all the pole pairs. Thus, no equalizer rings are required in wave windings. The terminologies for the winding design, such as the back pitch YB, the front pitch YF, the resultant pitch YR, and the commutator pitch YC, are displayed for wave windings. Considering a 4-pole machine, the simplex type of wave winding is illustrated on the screen as a second coil end traveling once around the commutator is connected to a commutator segment just ahead or behind that of the starting end of the first coil for progressive and retrogressive type winding, respectively. The commutator pitch YC for the progressive and retrogressive simplex windings is given on the screen, where C is the total number of slots and P is the number of poles. For the duplex wave winding of a 4-pole machine, the second coil end is connected 2 segments ahead or behind of the starting point for progressive and retrogressive type winding, respectively, and the commutator pitch changes accordingly. For winding a wave type armature, there must be a combination of a particular number of slots and conductors in the armature. Practically, it is not possible to meet such design requirement. Thus, to provide mechanical balance to the machine, one or more coils may be inserted in the appropriate slots, electrically insulated to other windings. Such coils are called as dummy coils. As we have seen in the wave-type winding, the coils are connected in series. Hence, the voltage of each winding gets added, but the current remains the same. Therefore, this type of armature winding is used in applications requiring high voltage and low current, such as the hand-cranked Mech ohm meters for providing high test voltages. Let us summarize through a comparison between the lap and wave winding, which we have learnt so far. In lap winding, all the coils generating EMF in the same direction are connected in parallel, whereas in the wave winding, the coils carrying current in the same direction are connected in series. Hence, lap winding is also known as parallel winding, whereas wave winding is called as series winding. In lap winding, the number of parallel paths A is equal to the number of poles P, whereas in wave winding, the number of parallel paths A is equal to 2. Lap windings require equalizer rings for better commutation, but wave windings doesn't. Dummy coils are not required in lap windings, but they may be used in wave